Hi everyone, in the lecture 4, we will study the equilibrium state of a p-n junction quantitatively. The lecture 4 has only one part, part 1, which is devoted to the depletion approximation. Draw the charge density due to the dopant atoms, electrons, and holes as functions of the position. Certainly, this diagram does not show the solution. In this case, in the n-type region, the electron density is equal to the donor density. Also, the hole density is equal to the acceptor density in the p-type region. Due to the strong diffusion at the junction, the net current flows. It is not acceptable at equilibrium. Therefore, we need an electric field to counterbalance the diffusion mechanism. Then, what is the appropriate direction of the electric field? As stated in the previous video, the direction from the n-type region to the p-type region is the correct one. It can prevent the diffusion of both electrons and holes simultaneously. Also, it is obvious that the electric field has a considerable magnitude only near the junction, since the diffusion mechanism is relevant only there. Shortly speaking, we must have a localized electric field near the junction to satisfy the equilibrium condition. Since the electric field flows from the positive charge to the negative charge, the n-type region near the junction should have a net positive charge density. On the other hand, the p-type region near the junction should have a net negative charge density. Of course, the total numbers of negative charges and positive charges are exactly matched. Then, how can you have a positive charge in the n-type region? Since we need positive charges, the first candidate is the ionized donor atoms, which are positively charged. However, they are immobile. They cannot move. Instead, we can consider the electrons. They are mobile and negatively charged. The absence of electrons can solve this situation. As shown in the figure, a region without electrons has a net positive charge density. Similarly, in the p-type region, there occurs a region without holes. Now, according to the above discussion, a region where both the electron density and the hole density are quite low occurs. This region is very important and has its own name. Its name is the depletion region. An important quantity is its width. How wide is it under given dopant densities? Let's calculate it together. Before deriving some equations, let's have a look at this numerical example. In this example, the donor density is 3 times 10 to the 17 per cubic centimeter and the acceptor density is 2 times 10 to the 17 per cubic centimeter. The y-axis variable is the net charge density. As shown in the figure, the depletion approximation is not perfect but quite good. Depleted regions are found in both the n-type region and the p-type region. The total depletion width can be obtained by summing the depletion width of each region. These two widths are not independent. For the charge balance, the total charge in the n-type region Nd times Wdn should be equal to the total charge in the p-type region Na times Wdp. This relation will be useful in the later derivation procedure. On the given space charge density, we can solve the Gauss law. Starting from the left side, in the n-type region with a positive space charge density, the electric field is increased. In the p-type region, on the other hand, the electric field decreases because of a negative space charge density. Analytic expressions for the electric field are shown here. You can check that two expressions give the same result at the junction x equal to 0. The electrostatic potential inside the semiconductor can be obtained by integrating the electric field. Since we have analytic expressions for the potential, the answer can be easily obtained. When we perform the integration, an integration constant is introduced. In this case, we have two integration constants. One is the electrostatic potential in the n-type region far away from the junction. The other is in the p-type region. Let us define the built-in potential, which is the potential difference across the junction. At the junction, two curves for the electrostatic potential in the last slide must meet together. By using this factor, the depletion width can be written as this form: square root of some quantities. Note that epsilon silicon and Q are given parameters. Also, we know the dopant densities. Therefore, the remaining task is to identify the built-in potential. What is phi minus infinity? What is phi infinity? How are they determined? We will use the following relations between the electrostatic potential and the carrier densities. These relations are valid only at equilibrium. The thermal voltage V sub T is about 25.85 millivolt at 300 Kelvin. By using these relations, we can easily find phi minus infinity and phi infinity. By combining them, the built-in potential is obtained by this form. The built-in potential depends on the dopant densities. When the donor density is 10 to the 20 per cubic centimeter and the acceptor density is 10 to the 17 per cubic centimeter, the built-in potential at 300 Kelvin is about 1 volt, and the depletion width is about 115 nanometer. Moreover, the depletion width in the p-type region is much larger than that in the n-type region. In other words, the depletion regions mainly appears in a relatively lowly doped region. For p plus n junction, the depletion occurs mainly in the n-type region instead of the p-type region. Up to now, the depletion approximation of a p-n junction has been studied. The carrier diffusion is suppressed by a repelling electric field, the built-in field. In this case, the current density vanishes. Then, what happens if the electric field becomes even stronger? Or what happens if the electric field becomes weaker? This topic will be discussed in the next video. Thank you.